Hello students, welcome to another video. From today we will start the another paper of T.Y.B.Sc mathematics, which is metric spaces. Metric spaces. This is some theoretical paper. This is the theoretical paper. Till now in our channel we have seen the whole syllabus of number theory of T.Y.B.Sc. So that paper was calculative, and now we will start the another paper of T.Y.B.Sc mathematics, which is metric spaces, and this paper is theoretical paper. So we will start the first chapter. Chapter first is Introductory Concepts. Introductory Concepts. Introductory Concepts. This is the first chapter. This is just introduction of some definitions of metric spaces and another definitions. So first, in the first chapter we will see the definition of metric space and various another definitions, so on which the rest of the syllabus is depend. Now the first topic is definition of metric space. In today's lecture we will see the definition and some examples on metric space. Definition of the metric space is let capital X be any non-empty set, X be any non-empty set. Then a function D, small d, from X cross X. This is X cross X, that is the cross product of this non-empty set X cross X to R plus union singleton 0. R plus union singleton 0 means set of all positive real numbers including 0. This function D is defined on cross product of this set X, that is X cross X to R plus union singleton 0. This function is said to be metric on a set. This X is function is said to be metric. This function is said to be metric on a set X. This function is said to be metric on this set X if this function satisfies following three properties. If it satisfies following properties. First property is non-negativity, that is whenever we apply the function on the elements of X cross X. So here the domain is X cross X being in non-empty set, and the codomain is R plus union singleton 0, that is the set of positive real numbers including singleton 0. So this function is said to be metric on this set X whenever this function satisfies following three properties. First property is non-negativity. Now D of elements of this set. So elements of this set are order pair, since this is X cross X, that is in the F.Y.B.Sc at up to S.Y.B.Sc level we have seen, suppose X and Y are two axes. Suppose this element 1 is just the element of the set, this X cross Y. So here X is non-empty set and this set X cross X is just the another set such that X, the elements of this order pair, suppose this XY is the element of this set, since this set of cross product. We know that the elements in this set of cross product are order pairs. Now first property is non-negativity. If we apply D on any element of this set, then that D of XY, that is the image of any element in this set, must be greater than or equals to 0 for all X comma Y belongs to X. Since this X belongs to X, again Y belongs to X is only one set, so distance of XY must be greater than or equals to 0. Metric space. In the metric space we have, and up to this first property we have seen that D from X cross X to R plus union singleton 0 is said to be metric It is not metric space. It's said to be metric whenever this function satisfies following three properties. Now, this function is a distance function. That is distance between any two elements of this x cross y. D is distance function, and another property, so sub property of this distance of x and x, that is distance between any single point. Suppose for example this is some space in which this is suppose x cross y. Then if we apply the function, then the distance between this small element x and small element x is at his place, and we are calculating the distance of x from itself to that point x, that is x is at constant situation and there is distance in between x to x is 0, since this x is only one point. So distance between x and x is equals to 0 for any x belongs to that set x. And first property was distance between any two elements x and y must be greater than or equals to 0. We are calculating distance, so if we find x to y distance or y to x distance, that will be the distance between x and y, and that distance must be greater than or equals to 0. This is the first property. That property is called non-negativity. First property, non-negativity. Write that non-negativity here, and after that write this first property, non-negativity. Non-negativity is our first property. Second property is symmetric axiom, that is distance between x and y is equals to distance between y and x. Here just explain few moments ago, that is the distance, if we calculate the distance from x to y or calculate the distance from y to x, that distance must be same for any xy belongs to x. Distance between x and y and distance between y and x must be same, and this property is called symmetric axiom. Symmetric axiom. This is second property. And third property is triangle inequality. You are familiar with the triangle inequality, that is the distance between, suppose this another element z is there, then the distance between suppose x and z is either less than or equals to this summation of distance between x and y and distance between y and z. So this forms a triangle, so that's why we call it as triangle inequality. Distance between x and z is less than or equals to distance between x and y plus distance between y and z, that is the sum. Distance between x and y must be either less than or equals to the summation of these two sides. So for any x, y, z belongs to z, that is all the elements of this set x cross x satisfies these three properties, must satisfy this property. Then we call this D is metric on set x, and this third property is called triangle inequality. And if then this D is called metric on set x, and therefore if this D satisfies all these properties and D becomes metric on x, then the space x on which D is applied, therefore the set xD, set x on which D is applied, the set xD is called metric space. It's called metric space. For example, this whole space x and on which this function D is applied such that D satisfies all these properties, then this D is called metric on x, and this both together x D is called metric space. So this is the definition of metric space. So this function on a non-empty set x is said to be metric on x if that function satisfies all these three properties, and if that function satisfies all these three properties of x, then that set xD is called metric space. So this is the definition of metric space. Now we will see one example of metric space. That will make this definition more clear. Suppose capital X is equals to R, that is set of real numbers. Here definition is, in the definition here we have used the notation X. So if X is equals to R, then clearly this R is non-empty set, and define the function D, and define the function D from, now the function D from X cross X, that is cross product of X. Now here X is equals to R, so that function must from R cross R to R plus union singleton 0. R plus union singleton 0, as this function defined as distance of xy. Distance of xy is equals to mod of x minus y. This is the metric. Suppose, and show that, first of all we will complete the question. Show that D is metric on R. D is metric on R, not D is metric space. D is metric on R, or RD is called metric space. D is metric on R, and hence this R with D is metric space. So here we have given that set X is equals to set of real numbers, and function D is defined on the set R cross R as distance of xy is equals to mod of x minus y. This is the usual metric or standard metric. If we have given the real line and we have to calculate the distance between any two numbers, then we take the modulus of subtraction of this a and b. For example, suppose this is the rapport, that suppose this 0 and suppose this number is 5. Then distance between 0 and 5, like clearly we can say that 1, 2, 3, 4, 5 is the distance, but we calculate that distance by using summation mod of 0 minus 5 or 5 minus 0, and that will be modulus of 5 is 5, and again modulus of minus 5 is minus 5. So sorry, plus 5. So 5 is the distance between 0 and 5. Similarly, if you take suppose this 5 and this is suppose minus 1, then to calculate distance between 5 and minus 1, we take the subtraction of both 5 minus of this minus 1 is equals to 5 minus minus 1, 5 plus 1 is 6. So modulus of 6 is 6. So distance between minus 5 and 1, sorry, minus 1 and 5 is 6. So this is the standard definition of calculating distance in real numbers. So we have to show that this is metric. That is, we have to show this function D on R cross R to R plus union singleton 0 defined as distance of xy is equals to mod of x minus y satisfies these three properties. First is non-negativity, second is symmetric axiom, and third one is triangle inequality. So first of all we will show the first property. So to verify first property, we know that the modulus of any real number, that is for all a belongs to R, mod of a is always greater than or equals to 0. If a is equals to 0, then mod a is equals to 0. A is equals to minus 1, then modulus of a is equals to 1. We know that the definition of modulus, or we know that the definition of modulus is defined as modulus of any real number is always greater than or equals to 0. We have to show that distance of xy is greater than or equals to 0 for all xy belongs to R. For that, we have given that distance of xy is equals to mod x minus y. So we have to show that mod of x minus y is greater than or equals to 0. That will give us distance of xy is greater than or equals to 0. So for that, we have mod a is greater than or equals to 0. Therefore, for any xy belongs to R, mod of x minus y. So x and y are real numbers. So x minus y, subtraction of real number is again real number, and we know that the modulus of any real number is greater than or equals to 0. But this mod of x minus y is defined as distance of xy. That is, distance of xy is defined as mod x minus y. So mod x minus y can be written as distance of xy. That is, this mod x minus y greater than or equals to 0 means distance of xy is greater than or equals to 0, and hence Our first property is satisfied, that is this function is satisfies the non-negativity. Also we have to show that distance between x and x, distance of any number with that number is 0, and we know that also mod of x minus x, distance of x is mod x minus x is 0, and modulus of 0 is 0, that is distance of x with x is equals to 0 for all x belongs to R. Hence the non-negativity property is satisfied. Now we will show the second property. Second property is symmetric axiom, that is we have to show that distance of xy is equals to distance of yx. Second property is distance of xy is equal to distance of yx. So first of all we will consider distance of xy, and we will prove that that distance is equals to distance of yx. So for that we have distance of xy is defined as mod of x minus y, and we have to prove that is equals to distance of yx. So we have to prove that distance of yx is equals to mod y minus x. Now we can just rearrange this as this. So minus y plus x, just changing the positions of y and x, we will get this. Now if we take minus sign common, that is minus 1 from both sides, so we will get y minus x, and we know that mod of a into b is equals to mod a into mod b, that is mod of minus 1 into mod of y minus x. Since mod a into b is equals to mod a into mod b, these properties we have seen in the T.Y.B.Sc level. So mod of minus 1 is 1, so 1 into mod y minus x is mod y minus x, and by definition of metric, mod of y minus x is equals to distance of yx. Mod y minus x is equals to distance of yx, since this definition of distance of xy is equals to mod x minus y. Distance of xy is defined as this x minus y, so mod y minus x will become distance of y and distance between y and x. So therefore we get distance of xy is equals to distance between y and x for all xy belongs to R. Hence the symmetric axiom is satisfied. Now we have to prove the third property, which is triangle inequality. Our third claim, or we have to show that distance between x and z is less than or equals to distance between x and y plus distance between y and z. Now to prove this distance between x and y less than or equals to distance, we take the definition or consider the left hand side. Therefore, as the distance between x and y, applying the definition of distance of xy is equals to mod x minus y, we will get distance of xz is equals to mod x minus z. Now we can add and subtract any number from this, that is if we add y and subtract y, that is x, suppose minus y plus y minus z. X minus y plus y will become 0, and that will give again x minus z. So subtracting and adding y, we get x minus y plus y minus z. So this is under modulus, and we know that the property of modulus, that is mod a plus b, is less than or equals to mod a plus mod b. So this will give mod x minus y plus mod y minus z. Since mod of a plus b is less than or equals to this is less than or equals to mod a plus mod b. Using this property, here a is equals to x minus y, b is equals to y minus z. Mod a plus b is less than or equals to mod of a plus mod of b, and by definition of metric, that is the definition of function, mod of x minus y is equals to distance of xy plus this mod of y minus z is equals to distance between y and z. Thus from this we have distance of xz is less than or equals to distance of xy plus distance between y and z. Hence third property is satisfied. for all x, y, z belongs to R. Therefore, D satisfies this triangle inequality. Here, D satisfies symmetric axiom, and the first we have proved that D satisfies the non-negativity. Therefore, D satisfies all the properties of metric. Hence that D is metric on R. D is metric on R. That is, RD is metric space. RD is metric space. Hence, the first example is completed. In the first example, first of all, we have seen the definition of metric space. This is the definition of metric space. Definition of metric space. Definition tells us, for any non-empty set X, a function D is defined on x cross x to R plus union singleton 0 as function D is defined on x cross x to R plus union singleton 0, and this function is said to metric on x if it satisfies the three properties. First one is non-negativity, second one is symmetric axiom, and third one is triangle inequality. If our function D defined on non-empty set x cross x satisfies this property, then we say that this D is metric on x, or we say that this xD is metric space. In the first example, we have taken x is equals to R, and we know that R is non-empty set, and we have given the function D from R cross R to R plus union singleton 0 as D is defined as distance of xy is equals to mod of x minus y. This metric is called usual metric or standard metric. We will write after this example one note. So, we have to show that this is metric. This D is metric on R. First of all, we have checked the property non-negativity. For that, we know that to prove this, to show this is metric, we have to show that first property, distance of xy is greater than or equals to 0. But distance of xy is defined as mod x minus y, and we know that for modulus of any real number is always greater than or equals to 0. Here x is real number, y is again real number, so x minus y is again real number, and modulus of any real number is greater than or equals to 0. So we get mod x minus y is greater than or equals to 0. That is, mod x minus y is greater than or equals to 0, and that is the mod x minus y is equals to distance of xy. So distance of xy is greater than or equals to 0 implies that our function satisfies non-negativity, and also we have this distance between x and that itself, x is equals to 0. That is clear. That is because mod of distance of x and x is defined as mod x minus x, and mod x minus x is 0, modulus of 0 is 0. So first property is satisfied. In the second property, we have to show that distance of xy is equal to distance of yx, but distance of xy is defined as mod x minus y. Just rearranging this and taking minus sign common, we get minus 1 into y minus x, modulus of this minus 1 into y minus x, and this is mod a into b, and we know that mod a into b is equals to mod a into mod b. Using this property of real number, we get mod of minus 1 into mod of y minus x, and mod of minus 1 is 1. So just we get distance of xy is equals to mod y minus x, and mod y minus x is equals to distance of yx. If we take distance of yx, then distance of yx will become mod of y minus x, and hence distance of xy is equals to distance of yx, and therefore our D satisfies symmetric axiom. And third claim is, that is, we have to prove the third property as distance of xz is less than or equals to distance between xy plus distance between y and z. So considering this left hand side, that is distance of x and z is equals to, or applying the definition of D, if D is defined as distance of xy is equals to mod x minus y. Here notations are different. That is, distance of x and z is equals to modulus of x minus z, and adding and subtracting y on this modulus, that is in the modulus, that is x minus y plus y minus z. So adding and subtracting y, we will get the same as this. Now we know that mod a plus b is less than or equals to mod a plus mod b. Using this result, we can write this is less than or equals to mod a plus mod b. So hence we get distance of xz is less than or equals to mod x minus y plus mod y minus z, and which is equals to distance mod of x minus y is equals to distance of xy, and mod y minus z is equals to distance of yz. Here is less than or equals to sign, and after that I am writing the equal to sign because this step is equals to this step, that is mod of x minus y is equals to distance of xy plus mod of y minus z is equals to distance of yz. So these both steps, that is this step and this step, are equal to each other, and this less than or equals to is relation between these two steps, that is this and this. So this is the less than or equals to is relation between these two steps. This step, that is less than or equals to, just we are writing this number, that is mod of a plus b is, this is less than this step. So this step is greater than or equals to this step. So here less than or equals to sign appears only here, and but the right hand side will become our distance of x and z. If you carry this side until this, so distance of xy is equals to this, and this is equals to this, so distance of xy is equals to this. Similarly, this step is less than or equals to this step, and this is equals to this, so distance of xy will become less than or equals to mod of x minus y plus mod y minus z. And as this distance of x and y is less than or as the distance of x and z is less than or equals to this mod x minus y plus mod y minus z, using transitivity we get this mod of distance of x and z is less than or equals to this step, because these two are equal. This less than or equals to sign appears, that is this relation is between these two steps, that is the steps second and third, and this equal to sign is relation between these two steps, that is this, suppose this is some real number, that this real number is equals to this, and but this real number is greater than or equals to this number. For example, just take this rough work. Suppose distance of x and z is equals to suppose 3, and distance of this x3 will become, again instead of taking particular example I will take suppose this p is equals to some q, p is equals to q, and this q is equals to suppose r minus s, q is equals to r minus s, but this r minus s is less than or equals to suppose t, this r minus s is less than or equals to t. As this p is equals to q and q is equals to r minus s, this will give us p is equals to r minus s, since p is equals to q and q is equals to r minus s, so p is equals to r minus s, but this r minus s is less than or equals to t. So we can write it as p is equals to r minus s, and this r minus s is less than or equals to t, but this t again equals to suppose some k, t is equals to k. So we can write this equation as p is equals to r, but which is less than or equal, that is these both numbers are less than or equals to t, and t is equals to k. So we can write this p is less than or equals to t and t is equals to k, so we can write p is less than or equals to k. So this is just the rough calculation that you don't need to write. This is explanation for I am writing here equal to sign because these two are, that is this step and this step is equal, but this distance x and z is less than or equals to this. So similar, by using transitivity we can write distance of xz is less than or equals to this, because they both are equal. This is just the explanation of rough explanation of this step. If you still not get what I am trying to say, just recap of, just again listen or just look over this explanation. So you will get why I am writing this equal to sign, and after that distance of xy is less than or equals to this. So hence the first example is completed, and this first example, write one note after this. This metric that we have put, that d is metric, this metric d is called standard metric or usual metric. This metric d is called, this metric d means distance of xy is equals to mod x minus y defined on R. It's called standard metric standard metric or usual metric or absolute value metric. Absolute value metric. Absolute value means modulus. Absolute value metric. So if the question is asked for 5 marks, prove that the standard metric is metric on R or usual metric is metric on R, or prove that D is usual metric. You have to prove, you have to take distance of xy is equals to mod x minus y, and after that you have to write this whole solution. Hence the example is completed.